The Markthal stands at the heart of Rotterdam, surrounded by major city landmarks such as the iconic Cube Houses, the Central Library, and Binnenrade Square, and enjoys direct access to the city's transport network via the adjacent Blok station. As a pioneering model of urban multifunctionality, the Markthal uniquely binds a vibrant food market, diverse restaurants, retail spaces, and cultural venues with 228 apartments, including 24 luxurious penthouses, all housed beneath a dramatic horseshoe-shaped arch. Conceived by MVRDV atop a historically layered site, the building vertically integrates its extensive commercial areas, cultural amenities, and residential units to create a lively, cohesive hub. 3 basement levels offer parking for 1,200 vehicles. The ground and first floors support over 100 food stalls and restaurants, and the soaring arch above houses apartments with striking city views. This intricate layering is made possible through cutting-edge structural innovation, notably the continuous concrete arch and record-setting cable-net glass facades, enabling natural light and panoramic connections across the diverse internal functions. Markthal is thus an exemplary case of vertical city living, where housing, commerce, leisure, and culture are interwoven within a single, dynamic structure. Built on historically reclaimed land with groundwater just 3 meters below the surface, the construction of the Markthal presented significant geotechnical challenges. Instead of relying on deep anchors, which would have been both risky and complex given the unstable subsoil and high groundwater, the project team employed robust concrete strut frames as internal bracing. These struts stabilized the excavation by resisting lateral earth pressures and maintaining the integrity of the construction pit. To further counteract hydrostatic pressure and prevent potential hazards, the site was intentionally flooded. By filling the pit with water, engineers created inward hydraulic pressure that balanced the external forces exerted by the groundwater. After managing the groundwater pressure, the team constructed a massive 1.5 meter thick underwater concrete base slab. This slab provided a stable and watertight foundation upon which the rest of the structure could be safely built. After this foundation was secure, workers began the gradual process of dewatering the pit, a rate of about 3 centimeters per hour. With the groundwork firmly established, we now move forward to explore the architectural and engineering feats that shape the Markthal's distinctive arch, particularly the construction of the soaring arch roof. This phase demanded the use of tunnel formwork, temporary mobile shuttering, and meticulous sequencing to accommodate the curving apartments and communal spaces embedded within the arch. Enhancing the vast interior, the Horn of Plenty artwork animates the 11,000 square meter ceiling, exemplifying the seamless fusion of engineering precision and artistic ambition that defines the Markthal. The first and second floors of the Markthal were constructed using the traditional reinforced concrete method. System copper bars were used to support the wide column spans and temporarily carry the loads of the freshly poured concrete slabs. At this stage, cable frames were also installed in preparation for the glass facade. These frames provide both structural support for the future cable net facade and contribute to the building's overall stability. From the 2nd to the 11th floors, the residential arches of the Markthal were built using the tunnel formwork method. Unlike conventional reinforced concrete construction, tunnel formwork enables the simultaneous casting of both walls and slabs. This method was ideal for the repetitive, arched residential units. The all-in-one process improves the uniformity and quality of construction while significantly increasing speed. Additionally, tunnel formwork yields high structural stiffness and reduces curing time compared to traditional methods. Structural cores and tunnel formwork walls play a primary role in both vertical load bearing and lateral load resistance. The core structures and tunnel-formed walls collectively transfer gravitational loads to the foundation. The slabs, created with the tunnel formwork method, provide horizontal stiffness, enhancing the building's overall stability. In this system, the tunnel-shaped walls act similarly to shear walls, but with greater continuity, which means that the structure responds effectively to horizontal loads, such as wind and seismic forces, without the need for many additional, separate shear walls. The high rigidity and inherent torsional resistance of the tunnel formwork system allow the building to resist lateral forces efficiently and as a unified whole. The construction began with the establishment of precise baselines and foundation settings, employing advanced 3D modeling and laser surveying equipment to ensure meticulous positional accuracy along the arch's complex geometry. Tunnel formwork, composed of rigid, reusable metal molds, was installed at both ends of the arch, allowing for the simultaneous fabrication of 4 cells per day, 2 from each end. The formwork itself was engineered to accommodate micro-adjustments, ensuring perfect alignment with the evolving curve of the arch. After site levels are ensured, the main vertical panels are first assembled on the ground near the working area. These include the form face and back structure. It is essential to ensure that the panels are square and properly braced to maintain alignment during installation. Following this, jack props or hydraulic jacks are installed. These allow vertical and lateral adjustment of the panels and helps precise positioning. Wheel supports are then assembled at the base. It is important the wheels are properly aligned and locking mechanisms should be fully functional. Push-pull props or alignment struts are installed to control the verticality of the panels during erection. These supports help adjust and maintain the formwork's plumb condition. Next, the deck panels are assembled. This forms the slab portion of the tunnel structure. Drill holes for the lifting beam in the right height. It is important to ensure that these holes are structurally sound and positioned according to design specifications. The lifting beam or spreader bar is assembled and attached. The rigging should be checked to confirm proper load distribution and safe lifting angles. Lift the carriage and gently roll, slide it into its starting bay. Lower and lock wheels. Once the form panels are positioned and braced on site, check their verticality using spirit levels, lasers, or plumb bobs. Adjustments are made using the push-pull props to ensure precise alignment before concreting. Finally, connect 2 panel halves to form a complete tunnel form cell. This is done using tie rods. 2 mobile cranes were utilized for repositioning, removal, and repositioning of these heavy formwork, optimizing workflow and minimizing downtime between cycles. The initial layout is laser verified, and support platforms are set to predefined tolerances. Steel tunnel forms are moved into position using cranes, then micro-adjusted to follow the arch's incremental curve. High-strength rebar grids are carefully installed within the formwork for both vertical walls and horizontal slabs, ensuring fabric continuity at construction joints through tightly controlled overlaps. Concrete is cast into the paired wall and slab forms in a single operation, with internal vibrators preventing segregation and voids. Winter conditions in the Netherlands necessitated heated coverings and real-time monitoring via maturity sensors to manage curing rates and prevent weather-related delays. After the concrete has cured to the required strength, the tie rods are released in preparation for dismantling the formwork. The formwork is carefully dismantled and detached from the hardened concrete structure. The driving wheels or rollers are secured to ensure proper movement and stability during repositioning. Jack props are installed and adjusted to support the formwork vertically and laterally, ensuring proper alignment. Tie rods are inserted to lock the 2 form halves together, maintaining structural integrity during concrete placement. Reinforcement bars for the slab section are placed and tied in accordance with the structural design. The rebar is cleaned to remove any dirt, rust, or oil, ensuring optimal bonding with the concrete. After the concrete has cured to the required strength, the tie rods are released in preparation for dismantling the formwork. The formwork is carefully dismantled and detached from the hardened concrete structure. Immediately after form removal, construction joints, where fresh and existing concrete meet, are treated with grouting and additional rebar to ensure both structural continuity and water tightness. Waterproofing applications are conducted as needed to safeguard long-term durability. The tunnel formwork is moved to the next bay or section and reinstalled for the following concrete pour. Each cycle, consisting of formwork installation, Reinforcement, concrete pouring, and form removal can be completed in less than 24 hours under ideal conditions, with up to 4 cells built every day, 2 at each end. This continuous pace progressively shapes the arch from both ends toward the center. After each pour, joints at the interfaces between completed and newly cast sections are treated with grouting and reinforced to prevent cracking and ensure water tightness. A fundamental challenge was that freshly cast concrete lacks the strength to support construction loads immediately after pouring. To address this, system copper bars and shoring structures, modular vertical supports, were employed beneath the formwork and new slabs. These temporary supports remained in place until the concrete attained at least 70% of its target design strength, typically after a 7-day curing period, as verified by maturity assessments and on-site inspections. Only once sufficient strength was confirmed could the supports be safely removed and the construction process advanced upward or inward along the arch. A key challenge arises as the building's arch progresses upward. The tunnel formwork must follow the complex curvature of the roof. The forms are fine-tuned and aligned precisely to the arch's design, a process that is carefully monitored throughout construction. Furthermore, the unfinished concrete in newly cast cells cannot bear its own weight until sufficient curing. Temporary supports, system copper bars, and shoring are left in place to maintain stability, with removal only allowed once the concrete achieves at least 70% of its design strength. Maintaining the precise curvature of the market hall's arch throughout construction was both a structural necessity and an architectural imperative. From the earliest stages, stringent control over baseline and foundation layout was enforced to prevent small deviations that could amplify as the structure rose. As construction progressed upward, the tunnel formwork modules had to be carefully repositioned and finally calibrated at each step to follow the intended arch geometry. This level of accuracy was achieved through the coordinated use of advanced 3D modeling in the planning phase, establishing the ideal curvature and alignment, and continuous on-site laser surveying, which enabled real-time monitoring and adjustment during formwork installation, concrete placement, and post-pour assessments. Iterative feedback between modeling and surveying ensured that every new segment precisely matched the design, safeguarding the integrity of the arch and minimizing the risk of cumulative misalignment. As the construction of the arch progresses upward, the upper tunnel formwork sections float above areas without direct support from below. To address the resulting vertical and horizontal loads, a combination of steel pipe trusses and cable struts is employed as temporary shoring systems. These elements are anchored to lower, already hardened structural elements and steel platforms. The market hall's arch is erected symmetrically from both sides towards the center line. By constructing both sides of the arch simultaneously and in a balanced fashion, the loads and moments induced by the arch's shape and gravity are evenly distributed. This reduces asymmetric forces that could otherwise cause tilting, twisting, or buckling of the partially complete arch, even before the central keystone is installed. Only after both sides are equally advanced and the overall arch stability is assured is the central, final cell were constructed, closing the arch and allowing for the structure to act as a continuous compressive system. This approach stabilized the formwork and the arch. Under the projected keystone location, heavy-duty adjustable steel shoring towers were erected at the lower side. Mounted on rails and equipped with hydraulic bases, these towers provided precise height and leveling control while allowing controlled redistribution of loads during pouring and curing. The hydraulic system enabled real-time adjustments to counter any differential movements and to maintain strict geometric alignment. Spanning the void between the two arch halves, a custom-built steel truss gantry was assembled atop the completed 10th floor slabs. This large span structure supported the formwork for the keystone, as well as the substantial loads of wet concrete and reinforcement during casting. The gantry featured featured fine leveling mechanisms, including screw jacks and hydraulic leveling plates, allowing for millimeter scale alignment and controlled deflection management during the pour. The gantry itself was securely anchored to the stable sections of the arch, ensuring reliable load paths throughout the process. Achieving equilibrium before pouring was critical for the arch's structural integrity. Surveying equipment continuously monitored displacements with sub-millimeter precision, while hydraulic jacks on the shoring towers and truss gantry enabled micro-adjustments. Only after both arch halves were confirmed to be perfectly aligned and level was the keystone formwork closed and prepared for concrete placement. The keystone, a monolithic slab with two integrated 400 millimeter thick wall beams, was poured using a combination of in-situ concrete and prefabricated elements. Concrete vibrators ensured proper compaction, while particular attention was given to floor finish quality and the planning of surface penetrations to prevent stress concentrations within this critical element. Once the concrete cured to its specified strength, the keystone locked the two sides of the arch into a continuous, self-supporting structure. Temporary supports, including steel pipe trusses, cable struts, and shoring towers, were then removed in carefully staged sequences. Load transfer was meticulously managed during this process to preserve equilibrium, with each support being released only once surveying confirmed safe redistribution of forces through the arch's permanent compressive load path. In summary, the successful realization of the Market Hall's upper arch relied on a sophisticated orchestration of temporary supports, balanced construction sequencing, precision surveying, and carefully timed keystone closure